Welcome to Study Life. In current electricity, we've been dealing for a good number of time and working with resistors. We have studied something called as color coding of resistors, and that was only to understand the value, the resistance value of a resistor. Right? But there can be certain scenarios wherein you will have to calculate resistances like giga ohms, mega ohms, and a bigger value of resistance, and that would be very difficult with color coding. So what are the other techniques? One such technique is using a Wheatstone network. What does a Wheatstone network look like? It basically looks like this. This is my Wheatstone network. What can you see here? You can see there are four resistances, the blue ones. Okay, let me just name them as, this is my first resistance, let's say R1. Okay, this is R1. In here I can see R2. What is R2? The second resistance. This here I can write it as R3, that is my third resistance, and over here this is my fourth resistance. So I've got four resistances connected in such a fashion that they form a quadrilateral. They form a quadrilateral, you can see, right? I'll just name this quadrilateral as, let's say this point is A, this point over here is B, this point over here is C, and this point over here is, let's say, point D. Can you see? A, B, C, D, right? There's an arm BD. There's another arm AC. AC and BD are called as conjugate arms. What are AC and BD called as, bacho? They're called as conjugate arms. You can also see a galvanometer here, right? This is a galvanometer that is connected between points B and point D. What is a galvanometer? A galvanometer is a current sensitive device that even shows a deflection to a very minute amount of current. It's a very current sensitive device. So every time you use a galvanometer, you will easily get the measurement, or not the measurement, but the detection of current in any network. Okay? This entire scenario is connected to my battery with an EMF E. For people, you can use a key, a rheostat, and lot many other devices, but this is the foundation of a Wheatstone network. I repeat, it consists of four different resistors connected to form a quadrilateral, a galvanometer that is connecting points B and point D. There's something called as balancing condition. What is balancing condition? They say that the current flowing through the galvanometer is supposed to be zero. The current that is flowing through this galvanometer is supposed to be zero. And when is this possible? That this is only possible when the potential of point B is same as the potential of point D. That means the potential difference between points B and D is nothing but zero. The potential difference between the point B and the point D is zero. Under such conditions, this ratio R1 upon R2 becomes equal to R3 upon R4. This ratio is achieved only when VB is equal to VD or VBD is equal to 0. This is something very important, and you have to prove this. You have to prove this now. So what are we supposed to use? We are supposed to use Kirchhoff's voltage law. We have learned in the previous videos how to use Kirchhoff's voltage law in any scenario. So without wasting much time, let's just directly dive into it. Let me just consider my first loop. What is my first loop? My first loop is A, B, D and A. My first loop is bachcha kitna? My first loop is A, B, D, A. Okay, let's work with what happens here. In here, I assume there is a small amount of current. What is the small amount of current equal to? I. At this point A, I understand that current divides into two parts. In here, in the upper branch, the current that flows is I1, whereas in the lower branch, the current that flows is I2. Okay? Ab dekho. I1 flows in the upper branch into the wire AB through the resistance R1. Thereby, a potential difference of I1 R1 is achieved across resistance R1. Similar terms, current I2 passes through R3 and a potential difference of I2 R3 is created across R3. Let's focus in here. I understand that there is a galvanometer here, and therefore some amount of current has to flow through this galvanometer. Let me just call it as IG. IG is the current flowing through the galvanometer. So if I1 passes through here, Ig flows downwards. What is the remaining current through R2? What is my remaining current through R2? It is I1 minus Ig. What it is? I1 minus Ig, and therefore a potential difference of I1 minus Ig into R2 is created across R2. Similarly, you can also find out what is my potential difference across R4. How would I do that? Here it is I2 and here it is Ig flowing towards B. At point B, both I2 and Ig meet and the same current flows towards C. Yes, exactly. So I understand that the potential difference of I2 plus Ig into R4 is created across resistance R4. That is simple, very easy, not too difficult. Once you have understood this, what should be my next step? Working on this loop. Let's walk from A to B. Along AB, there is only one potential difference, and how much is that? Yes, it is I1 R1. Okay. From B to D, how much is my potential difference? Ig into G. We know, right? Potential difference is equal to I into R. Therefore, it is Ig into G. I'll just write the potential differences. Okay, let me walk from D to A in this direction. Okay? What is my potential difference? I to R3. Do I return back to A? Yes. Therefore, this entire thing is going to be equal to 0. What happens next? The next step is to assign signs positive and negative to all these potential differences. Let's see. When we are moving from A to B, we are basically moving from the positive terminal to the negative terminal in the direction of current. And when we are moving in the direction of current, my polarity for potential difference is negative. Again, when I am moving from B to D, I am again moving in the direction of current. And when I am moving in the direction of current, my potential difference is again negative. Okay, now let's move from D to A. Current is going downwards, but my measurement is going upwards. Are they in opposite directions? Yes. So when they are in opposite direction, potential difference क्या हो जाएगा बच्चों? Yes, positive. Can you see this? So this is how we work KVL on this loop. I'll do simple things. I'll shuffle up everything that is negative to the other side so that it becomes positive. So this is I2 R3 becoming equal to I1 R1 plus Ig into G. Okay? So I'm going to box this up because I'm going to use it later. Let me mark this one as equation number 1. Yes. So that was our first loop. Let's walk into our second loop. Our second loop is B, C, D and B. What is my potential difference across BC? In loop BCDB, my potential difference across BC is I1 minus Ig into R2. Let me just write it down. I1 minus Ig into R2. Okay, let me walk from C to D. What is my potential difference? I2 plus Ig into R4. Yes, it's I2 plus Ig into R4. Okay, let me move from D to B. What is my potential difference? Ig into G. Ig into G, and since it closes at point B, this is equal to 0. What next? Okay, when I move from point B to point C, am I flowing in the direction of current? Yes. So if I am moving in the direction of current, what should be my sign? Negative. Okay, let me walk from C to D. Current is flowing from here to there, from D to C. I am measuring from C to D, opposite directions, right? So when it is opposite directions, it is positive. Okay, let me walk from D to B. Okay, current is moving from B to D. I am walking from D to B, opposite directions, positive. Let me shuffle up everything negative to the other side. Okay, so what do I get? I get it this way. I2 plus Ig into R4 plus IgG is equal to I1 minus Ig into R2. Mark this as equation number 2. Mark this as equation number 2. So I now have two expressions. What am I supposed to do? I am supposed to equate Ig as 0. So what should be my next step? My next step is substituting everything in equation 1 and 2 that has got Ig as 0. So only thing that is left here is I2 R3 is equal to I1 R1 and I2 R4 is equal to I1 R2. Okay? So what happens next is we are going to get a ratio and we'll start now. I've created two equations. I1R1 plus IgG is equal to I2R3. This was our equation number 1. What we created in our previous board. That was for the first loop, A, B, D, A. But when we created B, C, D, B, we got something like this. What was that? It was I1 minus Ig into R2 equal to I2 plus Ig into R4 plus Ig into G. This was what we derived in our previous board. What is my job now? In order to obtain the balancing condition, I will have to substitute Ig as 0. So if I decide on to substitute Ig as 0, my equation 1 changes and becomes equal to something like this. What happens to equation 1? Substitute Ig as 0. This becomes I1R1 equal to I2R3. So if I decide to calculate I2 divided by I1, if I decide to calculate I2 divided by I1, it has to be equal to R1 divided by R3. This is my equation number 3. What happens if I substitute Ig as 0 in equation number 2? If I substitute Ig as 0 in this equation, here I am going to only have I1R2, and on this side I am only going to have I2R4. And if I decide to calculate I2 upon I1 again, so I2 divided by I1 becomes equal to, what is it? What it is? Yes, R2 divided by R4. R2 divided by R4. So let me just box this and equate equation number 3 and 4. Okay, so let me just overwrite this so that it becomes very much clear to all of you. Can you see? Yes. I hope everything is perfectly visible and every one of you has understood everything that I have spoken. Let me just equate equation 3 and 4. R1 upon R3 is equal to R2 upon R4. Shuffle up things over here. What do you get? You get R1 by R2 is equal to R3 upon R4. Isn't that our balancing condition that we have decided to prove in this video? Yes, exactly. So Wheatstone's network is basically based on making the potential of point B and point D same, the potential difference between point B and point D 0, the current flowing between them 0, and therefore the ratio R1 upon R2 is equal to R3 upon R4. We are going to use this Wheatstone network principle into various applications like the meter bridge, the Kelvin's method, and many more in our upcoming videos. So I want you people to stay tuned with me, keep learning hard, keep getting focused more and much better, and keep working with me on Study Life.